I'm going to be talking about a peer project that will finish this summer, and it's on the topic of regional scale liquefaction modeling. So I think the motivation is pretty simple. Liquefaction is obviously a problem, but it is very difficult to predict at regional scale. It is simply hard to know what is beneath the ground and how it will respond without going into the ground. We can only afford to do that at a relatively small number of locations. In my view, there are three tiers of liquefaction model. The first would not use any subsurface data. It would use geologic maps, freely available geospatial proxies. This is usually what we're resigned to using in regional scale studies. This would be a model like HAZIS. Another example would be Rishidian and Bayes. This has been adopted in the SimCenter's R2D tool. It's been adopted by the USGS. And so here we're looking at one of their event cards, and we see the ground failure card. And if we open that, there is the Rishidian and Bayes prediction liquefaction probability. This is a logistic regression model. It uses 5 variables. It's trained directly on outcomes. And we're starting to see quite a few of this type of model coming on board around the world. Tier 2 would be the so-called stress-based models. These are models that do use subsurface test data. These are the state of practice models, the types of models that the NGL project is putting out. These models have been based on a few different types of test data, but most preferred would be the cone penetration test, the CPT. And so if we have CPT data, the data is used to predict liquefaction occurrence using any number of triggering models. And those results are commonly fed into a manifestation or consequence model to predict the cumulative or system response as manifested at the ground surface. If we take just one of these as an example, the Liquefaction Potential Index, or LPI, it's been around for almost 40 years now. People have studied case history data where they can compute the LPI, and they have trained fragility functions to predict consequences conditioned on LPI. So the probability of ground deformation or pipeline failure, foundation damage, etc. So this is the sort of thing you can do when you have in situ data. Tier 3 would be our constitutive models used with numerical methods. These could provide some additional insights spatially, temporally. This is not our focus. We're going to be looking at the intersection of Tier 1 and Tier 2. I'm going to argue in just a moment that there's a few major limitations with our current regional scale models. And so our question is, how can Tier 2 data and Tier 2 models be used to address those limitations? So my goal is founded on 3 perceived limitations of current models. The first is I don't think they exploit the available geospatial information. It is really difficult to predict what's below ground without going into the ground. It must require more than 4 or 5 parameters. Number 2, I don't think they benefit from the knowledge of liquefaction mechanics that we have. A lot has been learned. These models really don't look to learn from or anchor to the current state of practice models in any way. Number 3, they're not informed by or anchored to subsurface test data. We increasingly have a lot of subsurface test data. It's not hard to find places where a regional scale model gives a prediction that's drastically different than what the subsurface data would indicate. And so to not use all of that data seems like a lost opportunity. And so our goal was to come up with a Tier 1 model that addresses these limitations by mimicking or surrogating geotechnical models. And so when I talk about a surrogate model, I'm referring to using low order information to mimic the predictions of a high order model. I'll describe what we've done in 5 fairly simple steps. Step 1 is to get as much subsurface geotechnical data as we can. We have been focusing on CPTs. I think ideally in the future we would have SPTs as well. Most of our data is from Italy, New Zealand, followed by the United States. It isn't that there's not a lot of data in the US, it's just harder to get data here. We also spent a lot of time compiling data from several thousand geotechnical reports. So we did a lot of digitization. We've made the CPT data available. Seems like people are downloading it for their own uses. Maybe it's robots, I don't know. We'll see. Step 2 is to take each of these CPTs that we've compiled and to subject them to a range of seismic loading. For each value of seismic loading, we predict the liquefaction response using our state of practice model. So we predict triggering, and then we predict a manifestation index like the LPI. And so this curve that you see, this is a unique signature of a given site. No two places in the world have the same curve. And so if we could predict this curve without going into the ground, we would, in effect, have predicted the liquefaction response at that location for any and all earthquakes that could occur. And so towards that goal, we fit this curve with a very simple functional form with two fitting parameters. I'll call them A and B. And so A basically describes the liquefaction response at really high seismic loading, and B describes the sensitivity of that response, how steeply it rises. So we have done this for 3 different manifestation models so that we can ensemble or average them in the end. And these A and B parameters become our targets. So this is what we'll try to predict with machine learning. Step 3 is to compile a lot of geospatial information. We start with a library of about 75 different features. These are all things that are freely available that would hopefully have some correlation to subsurface traits. So these would be parameters of geology, geomorphology, hydrology, topography, ecology, et cetera, et cetera. We go through a feature selection process, recognizing that correlation is not always causation. Maybe we can use some of our domain knowledge to weed out some features. We usually end up using something like 35 or 40. And I'm mostly going to be talking about the results of some global models that we've trained, but we also trained a nation-specific model for New Zealand because they have some very high quality and unique predictor variables. And so we wanted to see just how good a region-specific model could be to inform whether it was something we wanted to pursue elsewhere in the world. Step 4 is to train machine learning models using these features to predict A and B where we know A and B, which would be the sites of our geotechnical tests. We then forward run the models that we've trained everywhere in the world, at least everywhere terrestrially, so that's more than 1 billion locations. I want to emphasize that this is very easy for the end user because all of the heavy lifting is done up front. The compilation of terabytes of predictor variables, the training, and then the forward running of the model, the user doesn't have to do anything that's difficult. Once we have these maps of A and B, as we do for the whole world, this information awaits ground motions from a specific earthquake of interest. And when convolved, we can predict the LPI or another manifestation index with very simple arithmetic. And so computationally, it's very easy at the end to run the model for a given earthquake. We can then combine that with a fragility function, whatever we're interested in predicting, ground deformation, pipeline failure, et cetera. And we can regionally predict impacts in a matter of seconds after an earthquake. And so here we're looking at the probability of ground failure. It refers to a specific severity of ground manifestation. So in terms of the performance of surrogating a model, how well do we mimic a geotechnical model? I can talk about the performance in A and B. I can say it's unbiased, but A and B don't mean anything to you. I can talk about the performance in terms of the manifestation index. And so we have an error of something like an LPI value of 5. And if you're a geotechnical engineer, this means a little bit something to you. Still, an error of 5 could be big or small depending on the actual value. You know, is the actual value 5 or is it 50? Those are very different errors. So I think really the performance only makes sense if you transform this into a consequence by using a fragility function. And so if we use a fragility function for probability of ground failure, we see that the mean error in our machine learning models is about 8% probability. And we see that something like 3/4 of the models are giving an error less than about 25%. So it seems like they do pretty good, but again, this is the performance mimicking a model. It's not the performance predicting liquefaction. And so we have to look at some other tests momentarily. All of our models, by the way, are bagged decision trees. We do try to use all of the different architectures provisionally to see what works well. It tends to be, in my experience doing geospatial modeling, that decision trees work very well. There is one final step, which is to update or anchor the machine learning to reality. So we know values of A and B where we have geotechnical tests, and we can do geospatial updating to correct the model. So this is an example in San Bernardino, just for example. And it seems in these cases like the machine learning model is generally doing pretty well. The little circles are CPT locations, and for some of them, we are under-predicting the liquefaction response. And so the local updating procedure is scaling up the machine learning predictions at some of the locations. So as for an example, this is an earthquake in Christchurch in New Zealand. The first panel is the Rashidian and Bayes model, the one that's in R2D currently. The markers are CPT sites where we know if there were or were not liquefaction manifestations, so the black sites there were. And in this neighborhood, most of the sites had liquefaction manifestations. So it seems like the Rashidian and Bayes model was under-predicting in this very specific neighborhood. It's giving probabilities of like 20 to 40%. The next panel is the machine learning model prior to updating. It's giving probabilities of, say, 60 to 80%, and you see a little more spatial nuance, and that's because there's more geospatial predictors. Here is after updating, and you see more spatial nuance added to the predictions. To be clear, the model is not reacting to what was observed, it's reacting to what the geotechnical data and models say at a given location. And so if you kind of compare the panels, you'll see in some places the prediction is scaled up, in other places it's scaled down. If your eyes find any places where things seem to be not working well, this is because the geotechnical models are failing us. And so it's obviously important that efforts like NGL continue to improve the geotechnical or the mechanistic models so that the models that we're aiming to surrogate are better. I will also just point out that we can take the variance that is produced by the updating process, and we can classify that to show people where the predictions are influenced by geotechnical data and where they're simply the predictions of machine learning. So we have put our products on Design Safe. We have these A and B maps for the entire world for these 3 different geotechnical models. We also have some example use scripts that can work in the Design Safe virtual environment. All a user would have to do is give the URL to a shake map from the USGS, which there must be millions, and it's quite easy. So to try to summarize some of the benefits of what we have done versus prior regional scale models, first of all, we're training on subsurface data, of which there are conceivably millions or tens of millions of subsurface tests. We're not training on liquefaction observations, which are pretty slow to grow. We're using machine learning, which I think can manage and exploit the predictive information hopefully pretty well. We're anchoring to geotechnical models, and so when we interpolate or extrapolate with machine learning, our existing mechanistic knowledge is guiding response and scaling. We update, so we anchor to reality. I mentioned it's very easy for users to use this model, to tell the world whether it works, to show us when it doesn't work well. And it's going to continually get better as we have more data to train on and as our geotechnical models that we're surrogating get better. So to say a little bit about performance quickly, we did a series of tests against the Rishidian and Bayes model. We used Breyer score, which is basically mean square error for probabilistic classifiers. And so 0 is what you want. And we did a few different things to establish statistical significance given the finite sample uncertainty. I won't really say what we did. I'll just tell you what the results seem to indicate. We also thought that our data could be spatially correlated. I mean, surely it is sometimes spatially correlated, and we were unsure how that might affect our significance testing. And so we tried some spatial resampling techniques to mitigate the spatial correlation. I'll just say up front that the correlation was less than we thought, and the results really weren't sensitive to this. So the first test we did was, and we did 3 tests looking at 3 different research questions. So the first was, does the model perform better in unbiased regions with 0 training data? We found data from 3 events that post-dated Rishidian and Bayes and where we had no training data. So Ridgecrest, Puerto Rico, Turkey. And we have the performance broken down by the 3 machine learning models, but then also an ensemble where we just took a straight average of the predictions. And so this test seemed to be saying that the machine learning model improved upon the RB20 model pretty significantly and to a large degree. The second test and question was, does updating improve the model's performance? For this test, we found a database of CPT case histories from 24 global earthquakes. And prior to updating, the machine learning model appears to outperform RB20 to a significant degree. When we do updating, the performance improves more. This is really not surprising. It is of course beneficial to go into the ground and get geotechnical data and use geotechnical models. If that wasn't the case, it would be pretty alarming. The third and final question was, does regionalization improve performance before updating? And so we have taken our global model that I've talked about so far, and we compared it to our New Zealand model for 3 New Zealand earthquakes. And the machine learning model, the global model, again, it seems to significantly outperform RB20. I should mention that a number of these tests have different types of bias, and so these tests are not fully unbiased. It's just difficult to exactly quantify, but so we have to take this with a grain of salt. Our New Zealand model does do better, but the improvement was, I would say, fairly marginal. And so it seems to us that the benefits of region-specific models are seemingly kind of counteracted by the benefits of learning from much more global data. So I will just say in the final minute here, some of the things we're doing in the last few months of our project. We want to get our maps integrated into R2D and integrated into the USGS information products. We've been running thousands of different scenarios through the models. So here's just a couple of examples in the Pacific Northwest, the types of scenario products we're putting out in various digital formats so that people can take and use them. We're interested in doing network modeling, joining forces with some structural colleagues who are looking at bridge damage, and we can bring now road damage due to liquefaction. So this is just a conceptual example in the Bay Area. And finally, once we have these maps, as we do, they permit performance-based analyses at national scale. And so we could hypothetically predict the return period of ground failure or foundation damage. We could do economic analyses for the entire country. So with that, I'm out of time, and I will just thank these individuals.